Great, thanks for coming to the What Happens When Things Get Warmer reunion tour. So, with Scott's introduction about looking around the room, I think one of the things I was struck with is, I've been very lucky when I came to Stanford that there were many communities that welcomed me and spaces that I was in. And I think there's people from sort of every one of those spaces. So my students are sort of half in electrical engineering and have been. And there are folks here from that. There's my own geophysics department where I have a lot of people who I share how we produce knowledge with. And my students and I get to really have a cozy educational research environment with people who deeply understand how we approach knowledge production to a variety of problems. I have close relationships and friends and mentors in earth system science who I've been on searches with and who've been a community that I share more topical commonality with, even though our approaches are different. And there's people in the Woods Institute who welcomed my whole family when we first moved here, and is a space where we think about impact and policy. And so I think maybe my favorite thing about the new school is that there's all these communities in one room, and as we become sort of more epistemologically pluralistic, we can support and celebrate all these spaces and ways of producing knowledge in our time of abundance. And so I guess given that, I would like to take you through sort of the particular epistemological approach my group takes to studying ice sheets. So I, like every other glaciologist you'll ever hear a talk from, start with plots like this about sea level rise over the next 100 years. This is the range of uncertainties in this particular set of models. This is where sea level is now. This is the height above which up to 4 million people could be potentially displaced. And then all these plots come with a disclaimer, unless the Western ice sheet collapses, and then don't trust these numbers. Given that significance and cost, why can't we do better than this? The main reason is the main tools we have to study ice sheets are satellites, and satellite observations at Earth cannot observe directly the subsurface processes that are governing change. So instead, we collect data, ice-penetrating radar data from airplanes, including this airplane that fought in the Battle of the Bulge and has this antenna underneath it that shoots radar down through the ice. The radar comes back. We record it on this antenna, which was made in a garage in Copenhagen in 1970. And then it makes plots like this. So this is 4-kilometer deep cross-section of the ice sheet. You can see the top of the ice, the bottom of the ice, the layers inside of it are depositional layers that are isochrones, so you can use them to date the flow of the ice sheet, like tree rings. And what mostly my field has done with this is grid this together. This is like 50 years of every single nation on Earth flying these airplanes. You make a grid like this of these flight lines. You make a map like this of what the continent would look like without the ice sheet on top, and then you run ice sheet models on this. And this is what gives you those numbers for the sea level projections. My group is focused mostly on not doing this, and instead is trying to actually use that data to analyze the subsurface conditions and processes that govern how the ice sheet evolves. And every single thing in this cartoon is something that my group or our collaborators or other people in my community are quantitatively analyzing the signals from the radar to constrain. And I'm going to walk you through some of those and what it's like. So initially, I'm going to talk about Thwaites Glacier, which you may have heard in the news. People call it like the Doomsday Glacier, this whole collaboration here with all these acronyms. You could only propose to study the glacier. And there's like, everybody had these acronyms like Tarzan and Ghost. And then one of the teams didn't have an acronym, and then they felt bad, so now they're Thor. And I'm involved in Time with Jenny Sakale as well. So okay, everybody's studying Thwaites, and its geometry, its position, its rate of change makes it one of the most unstable glaciers in Antarctica, and our best candidate for something that really could cause the whole Western Arctic ice sheet to go away. But even if you look at this plot on the left, you've got Thwaites and you've got Pine Island right next to it. And Pine Island's like the next most mass lossiest, unstabliest glacier after Thwaites. And even if you don't think about ice flow a lot, that area that is circled, that is weird for a flowing fluid. Like, I wouldn't draw a tumor of ice flow like that into Pine Island if I was just drawing it, right? If you think about like flowing honey or other viscous fluids. What is also weird about that area is if you look in the middle, that's a model of where subglacial water would flow. And you can see the water's flowing out of Thwaites, even though the ice is flowing out of Pine Island. This mostly also doesn't happen with glaciers. And so given that this is the boundary between two of the most important, potentially unstable glaciers, why don't we know why that boundary is there and where that area would flow? The answer from a cool point of view from an engineering side is that that sits at the boundary between that brown survey, which is a British survey, which was with 150 megahertz radar interleaving short and long pulses, and the purple survey, which is a Texas survey with a 60 megahertz radar with chirped pulses. So it was hard to correct those together. Fortunately, there was a reflight line flown, and through a lot of really cool signal processing we could talk about, we determined that that area in blue is low reflectivity because it is frozen. So that boundary is there because the bottom of the ice sheet is frozen to the bed. And ice can thaw. So that means that piece of the boundaries may be up for grabs, may change in response to warming. So if we go downstream from there, okay, maybe that top bit's up for grabs, but maybe the boundary between them isn't. So that black line there, these are the edges of ice flow. These are shear margins. You can see all the other black lines that I didn't circle match the topography. You could draw them there. But that black line crosses high topography. I would never draw that boundary there, right? So it is not topographic control on where it's flowing. So this is the TIME project that Jenny and I are both involved with. Two hypotheses, including based on Jenny's PhD work, is that maybe it is warm ice. That is why that shear margin is where it is. It's softer where it's warmer. Another is that it is perhaps ice fabric. And the two things to take away from this, on the left, my former student Nicole actually invented a radar system that could allow you to have wider offsets so that you could do tomography like a CAT scan and tell if you have warm ice in there. And a student just came back from camping on the ice sheet for 4 months making some of these measurements. On the right, those top plots are polarimetric signals. So like if you take the radar antennas and like spin around, and what is striking with that is the top is real data, and the bottom is analytic signals made by a former postdoc who did a PhD on fish optics and the way mantis shrimp use circular polarized light to like mate and fight with each other. And those patterns in pure analytic signals look a great deal like the data there. And so even though fabric is so small, we can test both these hypotheses with this system Nicole built. So okay, fabric temperature also may be up for grabs. So if we go further downstream, there's this one eastern ice shelf here in blue. You can see everything's red because it's all faster. Blue, that's slower. Maybe that will stabilize the boundary between the two glaciers. It happens to be the case on the right that two modern survey lines in purple and that orange line from the 70s, which is the only one in that whole quadrant of Antarctica, the only flight that was collected at that time, both crossed that ice shelf. So we have the potential to see change there. The optical film on which this was recorded, there were thousands of reels in the Scott Polar Research Institute at the University of Cambridge. Fortunately, we had a film scanner, and I had two friends who had studied art history who were somehow unemployed, who came with me for 2 weeks, and we scanned 2 million images, which actually there's now a website. If you go to Radar Film Studio, you can go and play with this film and help us QC it. It's years of endless fun. But after you do that, what you can do is you can directly compare that top line, which actually looks really beautiful for an old record with vacuum tubes from the 70s, to the bottom, and two things stand out. One, that area circled in red is the grounding, the piece of high topography in the ocean that's holding it back. You can see it is reducing on there, so it's going to come unpinned from that shortly. And you can also see the melt in the middle where there's those crevasses. It's not melting uniformly, which is what you would see from satellites. It's melting through faster in the middle. So probably this ice shelf doesn't have very long, next couple of years, next few years. So that's not going to stabilize it. So okay, one takeaway. Thwaites, Changius Glacier, right next to Pine Island, the entire boundary seems to be up for grabs of why that boundary is where it is. So maybe that will really change those projections. Okay, there's that. If you're like, okay, that's fine, that's sort of where we are now, what do you think might drive these changes? We could have given a whole different version of the talk with some of my other students' work, but these are candidates, I think, of what will govern either what will cause the change or how it will respond. One thing is, what is the geology underneath the ice sheet? Is it sediments or bedrock? And how will it retreat across that template? And my former student, Mickey, did some geostatistics there to try and classify that and compare it to the continental shelf. There are pieces of the bed that are frozen. We were just talking about that. They could thaw. What parts of Antarctica are susceptible to losing mass if a piece that is frozen and stabilizing it thaws? My current student, Eliza, has a paper that suggests it's actually this part of Antarctica over here, which is currently not changing very much. So that's a very interesting and provocative result. The other possibility is as things get warmer, not only does it have economic impacts, but you start to get surface melt on the surface. This happens in Greenland all the time. These are very dynamic processes in Greenland. Doesn't currently happen in Antarctica, most places. If Antarctica starts to do that, you could really change what's forcing things. And my former student Riley showed that there was this year, this extreme melt year in 2012 that made the news. And it was like all of Greenland is melting, but really it was just every piece of Greenland was above melting temperature, not that the whole thing melted. But shockingly, what Riley showed is you got this layer of melt that caused this ice layer you could see in the radar. And then what happened is normal years where water would infiltrate, sort of like rain in a, recharging in a desert setting. Now, once the water was in there, it hit this ice layer. And even normal years of water would pile up, make more ice, less good to percolate. And so it changed the whole system's response once it had one strong melt season. So if you're like, what governs the future? Maybe this. I said in the beginning my group is sort of half and half electrical engineers and geophysicists. So my group also invents new things. So going beyond these flights where you're in an airplane as a person interacting with racks of data, there are other ways we could collect data going forward. One possibility is if you want to understand these processes at a finer scale, there's a lot of ambiguity between if you see an echo, is it bright because of water on the bottom, or is it bright because the ice is cold, or is it crystal fabric? Separating, again, all these signals, like separating chemicals, requires a different sort of radar system. So my student Anna just came back from camping in Antarctica for like 4 months. She's developing a ground-based multi-frequency radar radiometer system that can really separate temperature signals from reflectivity signals and also separate bed roughness signals by measuring at lots of different frequencies. My former student Sean developed this passive radar sounding system, so he's really interested in saying, okay, sure, maybe you have a measurement in one spot, but we need to measure all the time. We need lots of sensors. And so his system was, rather than transmitting a signal, which takes a ton of energy, could you just listen to the radio environment ambiently and do autocorrelations with the electromagnetic signal, very similar to passive seismology, but just electromagnetically. And so what he was able to do is develop a system where you listened, in this case, to the sun, which is a nice broadband radio source, do cross correlations, and that top plot is a measurement to the bottom of the Greenland ice sheet, just using the sun as a signal, transmitting nothing. So once that's miniaturized, which will take some work, then you can have sensors sort of all over the place. Finally, my student Thomas, who was an undergrad in my lab, is developing drone-based airborne surveys. And I think this is a long-term evolution in terms of how we will collect this data and how we can move to a spatially pervasive, repeat pass situation. Thomas has managed as a PhD student to compete with like most of these international big research bodies by starting with these small styrofoam planes. Part of that was because of COVID, and we could only test over Lake Log, which is actually much harder from a permit point of view than Antarctica or Greenland. But it also has allowed him to really solve the antenna problem by embedding these antennas he built into the drone. So right now, that drone, it's in a suitcase, you go throw it, it will fly a pre-programmed flight path for 25 kilometers, come back and land. And I think the scaling up from this to big things that could replace big DC-3 crewed aircraft will be how we change how we collect this. And because Thomas was a Stanford undergrad, he's got like an acronym and a logo and a slide like this that makes it look like a startup. So there you go. This is the Peregrine. They're all named after like falcons or some California birds. But yeah, this is Thomas's drone. My hope as a group, as we develop these things, and when I think about students starting projects, is that we'll move from a single type of radar sounder to sort of an ecosystem of observations that give us sort of customizable coverage in space and time. The final thing I'll mention is everything I've talked about now, we're doing mostly from the air. I'm also a science team member on the Europa Clipper mission to Jupiter's icy moon. We have a dual frequency radar system there. What we're looking for is also a question about how temperature affects life. But in this case, can we find life elsewhere in our solar system? And so everything we've talked about here you could do to analyze the data. But in this case, with the airplane, you're using like a 10 kilowatt transmitter flying like 500 meters over the surface. At Europa, we'll be using a 10 watt transmitter flying hundreds of kilometers over the surface, very fast. And the only hope we really have there is that you can get through ice more easily when it's cold, and space is very cold. And so hopefully we'll get some echoes from the ice shell, find a nice salty pocket of water in there, and that's a spot we could go and look for life. And that's it.